All right. Okay, so first introduction to continued fractions. So the very first thing, I'm going to start at the beginning, and one nice thing is if you've got lost it basically in this course in any way, it's kind of a reset in that you'll get unlost because we're starting a completely new topic. And I think the only real background you need to know for this topic is you have to remember the, say, the Euclidean algorithm for long division and computing GCDs, which was from the first week or two. And then some basic stuff about GCDs. So the prerequisites kind of reset for our discussion of continued fractions. It's also nice because we can just prove everything carefully. There's no gaps or sort of random stuff, but there still are many open problems that appear once you learn the basic definitions of continued fractions, and also some excellent applications. Another nice thing about this continued fractions topic is that it may appear to be kind of this one little topic, but it actually is a special case of a lot of other things, and that at first, basically this generalizes in lots of interesting ways. So it's not just an isolated topic. Okay, so first I'll just start with a little observation, kind of a fun thing. So the golden ratio, 1 plus square root of 5 over 2, is equal to 1 plus 1 divided by 1 plus 1 divided by 1 plus 1 divided by... Take a while, but if you just keep repeating this pattern, natural pattern indefinitely, you'll get the golden ratio. So let me convince you of that. So first, what I mean by what I've written on the right is this is, by definition, the limit of the sequence whose first term is 1, whose next term is 1 plus 1 over 1, whose next term is 1 plus 1 over 1 plus 1 over 1, etc. So you get a sequence by truncating this at any point. It's a sequence of rational numbers, and to say that these two numbers are equal is to say that the sequence of rational numbers that I've listed right here, which you get by taking this big arithmetic expression involving divisions and pluses, and simplifying it, the sequence of rational numbers converges to the real number on the left. Okay, that's the claim. And now let me prove it to you. This is very, very easy to prove, as it turns out, using basic algebra. So let's do it. Here's what we'll do. This thing on the right, so the one thing I'll skip is that it converges at all. That's something we'll prove later. But let's assume that it converges, and then I'll prove that it definitely has to converge to the golden ratio. Okay? So let's just call it, whatever it is, x. I'm defining x to be whatever this limit is. And now let's just note, there's a simple identity. Notice that it's kind of recursive. This whole expression is sitting right here inside of itself. Right? This, I think I circled in red, this number, it's 1 plus 1 over 1 plus 1 over 1 plus. It's exactly the same as the original expression. So it's equal to x. So in fact, x is equal to 1 plus 1 over x. And so, assuming that this thing makes sense, we have this relationship between x and 1 plus 1 over x, and you can find x now using the quadratic formula. Simply multiply both sides by x, and you get x squared equals x plus 1. Or x squared minus x minus 1 equals 0. That implies that x is equal to negative of b plus or minus square root of b squared minus 4ac all over 2a, which is 1 plus or minus square root 5 over 2. On the other hand, whatever this limit is, it's a limit of positive rational numbers, so it's non-negative. So really, x has to be the plus version of this. So x is equal to 1 plus root 5 over 2, or the golden ratio. Okay, so this thing that I've written on the right is a continued fraction. It's an alternative way of representing a number in this particular instance. You can write a number like this in terms of algebraic stuff and radicals, or you can write it as this big fraction, in this particular case, as given, like this big infinite fraction-like expression. Here's another example of something. So here's a fraction, 103,993 divided by 33,102. If you write this quotient out, this rational number, in decimal, here's what it looks like. 3.141592653, and then 0, 1, 1, etc. So that digit is not the same as, so all the digits up to that point are the same as the digits of pi, right? Okay. So this is a good rational approximation for pi. Where does this come from? Is there a good systematic way of finding rational approximations to real numbers, which moreover will be guaranteed to give you the best possible rational approximation of a given size? I mean, there's lots of numbers with 6 digits, 5 or 6 digits whose quotient is near pi, but this one is a lot better than others that you might choose. So, for example, a naive one might be 31415 divided by, I guess, 10,000. That's a quotient of 2 rational numbers that has the property that at least the first 5 digits agree with the digits of pi. But it's like half as good. Even though the size of the numbers are about the same as what we have here, it's only half as good of an approximation. So continued fractions also provide an algorithm for finding the best rational approximations to real numbers. And they're provably the best ones, as we'll see. Okay, so how continued fractions. Okay, let me show you one more surprising looking example. So you know the number e, which is 2.718 ... the base of the natural logarithm. Turns out it's also equal to 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus, it's getting hard to write it like this, so I'm going to introduce some notation which will make it way easier. So just stop for a second. The only thing in this continued fraction that matters is the numbers right here. Everything else is 1. Okay? So let's introduce some notation, and then I'll go back to writing that. This is notation we'll use an enormous amount, so I probably shouldn't hide it behind that thing right here. Because we're just going to use this so much. Square brackets a0, comma a1, comma a2, comma a3, etc. This means the continued fraction a0 plus 1 over a1 plus 1 over a2 plus, etc. 1 divided by a3 plus ... Okay? It's simply a notation that's a little bit easier to write. It gets really hard to write this, especially if you had like 20 of them, or 30 of them, huge. And it's also hard to get everything sort of angled right, whereas this is very easy to write. So this means the same thing as that, okay? So rewriting this using the notation I just introduced, it's 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, guess what the next number is? Nope. 10, it is 10. Nice. 1, 1, 12, 1, 1, 14, etc. So you might know that E is a transcendental number, so you don't have any simple repeating pattern in the decimal digits of E. But, surprisingly, the continued fraction expansion of E exhibits a nice simple pattern. It's not it's not exactly just repeating over and over again, but it has an obvious pattern. This pattern does hold. Interestingly, when I mentioned this once when I was teaching this course a couple of years ago, I just sort of noticed this, and I asked one of the students in the class to try to find a proof, because we couldn't find anything. And he looked all around, he couldn't find any proof in any English literature. It was really weird. Even though it's obviously true, if you just do it to like 1,000, you can easily compute 1,000 of these using a computer, and you see that it's got to be true. But there didn't seem to be a proof anywhere, so he spent a lot of time trying to read some German proof, and then finally he found on some website of Henry Kahn, who was the director of crypto at Microsoft Research until a couple of years ago. He found a proof there, and he wrote it up, and that's one of the chapters in the book, which is a proof of this statement. And similarly, pi has a continued fraction, which looks like the following. 3, 7, 15, 1, 292, 1, 1, etc. So these continued fractions, you can kind of think of them as being sort of like an analog of a decimal expansion, but there's something more subtle about them in that you can have two different transcendental numbers, pi and e, and pi, its continued fraction looks bizarre. I mean, there's no natural pattern at all, whereas e has a really nice simple pattern. Yes?
That 292, is that where we get the 355 and 115?
Yeah, I truncated this continued fraction right here, and that's what I got. And if you think about it, you're always adding 1 plus 1 over that thing. So if you truncate it at a big value, then you're throwing away not very much. It doesn't change the result very much. So if you want to find a good rational approximation to a real number, you write down a continued fraction that should be somehow associated to the real number, and then you truncate it right after a big value. I haven't told you how to write down a continued fraction associated to any real number, but there's a simple algorithm which takes as input a real number and then just outputs a sequence of integers, the integers being the terms of a continued fraction that converges to that real number. That's one of our goals to see why that is the case. Okay? All right, so these are some examples just to give you a sense of why this sort of thing might be useful. One other remark, if you, let's say you have an algorithm that is supposed to compute a rational number. It's like the rational number, there's a lot of programs that output a rational number. I'm not gonna. Number 3, this comes up frequently. Here's an example. Remember when we were talking about elliptic curves, and we were looking at rational points on elliptic curves? So the coordinates are rational numbers. It turns out that there's a really, really amazing construction due to somebody named Hegner, which gives you a rational point on any elliptic curve by a purely analytic formula. It's like you sum some infinite series, and it gets closer and closer to some actual rational point in the curve. So that's pretty amazing. However, if you want to actually compute that rational point in practice, you don't get the rational point, you only get decimal approximations to it. So what do? You compute like 10 or 15 digits of the decimal approximation, then you write down a continued fraction that converges to that number that you just approximated, and then you look at it, and it'll typically look something like this, and suddenly there'll be a big term like this. So you truncate at the big term, or actually right before it, and then you get a rational number, and that rational number is very likely to be the one that you're really looking for. And then you can kind of check some other way to see if it's right. So many algorithms where you compute a rational number, what you do is, so you have some weird algorithm, it's supposed to output a rational number, but what it really computes is a floating point approximation to it. What you do is you take that approximation, which you can compute, and then you use continued fractions to find, with high probability, the rational number that you're probably approximating. And this means that you have to compute far less decimal digits of your number in order to get it than you would have to compute if you were to naively try to do something like this. This one little idea of continued fractions basically massively improves what you can do regarding computing rational numbers in various contexts. And there's a huge number of algorithms that involve, basically are algorithms that might have input an integer, let's say, output a rational, but along the, inside of the black box that is the algorithm, lots of floating point operations happen to make things faster. There's a program called GAP. It's an open source computer algebra program. GAP stands for Groups, Algorithms, and Programming. And in this system, they seem to they're mainly working with finite groups and discrete structures. And so they decided that they wouldn't have very good support for floating point numbers. And in their system, systematically, for many years at least, they had very bad support for floating point numbers, which meant many algorithms that take as input, or functions that take as input an integer and output an integer are rational. An amusing thing happens is that in many cases you can come up with massively better algorithms if you allow floating point numbers, even though the input and output are integers or rationals. And so they ended up having really, really slow functions for certain things just because they are sort of philosophically opposed to working with floating point numbers. So I don't know if, hopefully no GAP developers are offended by the comments I just made. But this happens a lot, and continued fractions play an absolutely critical role in this. Okay, so now we're going to systematically develop basic properties and foundation of continued fractions. So we'll prove a few things. One thing, let's assume always that a sub 1, a sub 2, etc., these are all greater than or equal, well, they're all greater than 0. They're all positive real numbers. And a0 could just be any real number. So we'll just make that assumption. Otherwise, it doesn't work very well. The theory doesn't work very well otherwise. Usually in practice, the a's will be integers. But you can make perfect sense of things with them being real numbers for most things that we'll do, and so allow them to be real numbers. And also, by the way, this whole theory that we're going to develop, there's an analog of it that's used for dealing with functions, which I think somebody in here's project is on, or will be on. Somebody here, the continued fraction project person? Yes. So this whole idea is useful not only for dealing with numbers, but for dealing with functions. Okay, so let's finally prove something. So first, another definition. Let's write Pn over, so this is in the special case when, let's see. Okay, so what I'm going to do, I want to just do some things, well, yeah. I'm going to define numbers p sub n and q sub n so that are an easy recursively computable, I'm going to define these in a minute. So our goal is to get a formula that looks like this. And this is basically going to replace the confusion that would occur if we tried to directly do huge amounts of algebra with expressions like this by something that's just much easier to work with. But gives us something completely equivalent. Okay, so I'm going to develop a little it'll just look like a purely technical little kind of thing, but it's super useful as far as making all the algebra just completely sort of trivial instead of impossibly confusing. Okay, so that's the point of what I'm about to do. So let's just define some numbers. So define numbers. P sub n and q sub n as follows. So the setup is we'll have, let's just consider for the moment a continued fraction given by a0 through am. And here we're going to do this for n between 0 and m. right? So you have a continued fraction with finitely many terms. They're labeled A0 through AM, and then for each n less than or equal to m, you can just truncate the continued fraction and take that first part. And I'm going to give you a formula for easy to compute numbers Pn over Qn, which if you compute them and then take the quotient, you'll get this continued fraction. Okay? And it's just, again, taking the algebra that would confuse us, involving working with expressions like this, and just turning it into a simple definition that allows us to prove everything we want to prove without getting confused. I hope. Okay, and let me tell you the definition, which is really fairly easy. It's a little bit funny at the beginning, but it's easy in a second. So I'll define these, actually, go all the way back to -2 just to make things really nice and clean. So P minus 2 is 0, Q minus 2 is 1. P minus 1 is 1, and Q minus 1 is 0. P sub 0, Q sub 0 are as follows: A1, A0, and 1. And now, in general, P sub n is just the product of A sub n and the previous one, P sub n minus 1, plus A sub, plus P sub, plus P sub n minus 2. And then with Q it's the same, so with Q's instead of P's. So Q sub n is A sub n, Q sub n minus 1, plus Q sub n minus 2. Okay, so this is a recursive formula. The first two terms, so the Pn and Qn for n equals -2 and -1 are just constant. They're always the same. P0 is always A0 and Q0 is always 1. And then afterwards, you get the Pn's and Qn's by simply taking An, multiplying by the previous one, and adding the one before that. It kind of looks like Fibonacci numbers, except there's A sub n's. In fact, what if the A sub n's were all 1? These would be Fibonacci numbers. So if you take the continued fraction for the golden ratio and look at the numerators of the partial convergence, you end up getting Fibonacci numbers. For what it's worth. Okay, so that's a definition. That's all this is a definition. But now what I'm going to prove, pretty obvious from what I put up there, is that A0 through An is equal to Pn over Qn. Okay? Once we have that, then instead of doing tons of algebra with these sort of big rational algebraic expressions, we can just use this definition and this fact. And everything we'll want to do will just fall out very easily from this for the most part, and induction. Okay? So any question about this statement? Right, so let's prove it. This one proposition is the most important thing I will prove, so don't get lost. So proposition, exactly what I wrote over there where I said goal. The continued fraction A0 up through AN is equal to Pn divided by Qn. Proof. So, so the proof is just it's a calculation using induction. It's not completely trivial. So it'll just be basically a careful calculation using induction. And so let's first do the base case. N equals, so I claim this for all n greater than or equal to 0 and less than or equal to m. So 0 less than or equal to n, less than or equal to m. So let's do the base cases. We'll do the first two just to be sure. So we'll check that this holds for n equals 0, n equals 1, and then by induction we'll see it holds for all n up to m. Okay? Here we go. So when n equals 0, what does this say? It says that A0 is equal to P0 over Q0. Geez, let's look at the definition of P0, Q0. Is it true or not? It's just true, because like P0 is by definition A0, and Q0 is by definition 1. So you're good. Okay, so that's true. Let's try n equals 1. So that says that a0, a1 is p1 over q1. Okay, so let's see. Let's figure out what p1 is. P1 is, we just use this formula. It's a1 p0 plus p minus 1. And q1 is a1 q0 plus q sub minus 1. But p0 is a0. This is a1 a0 plus p sub minus 1, which is 1. And this is a1 q0. q0 is 1 plus q minus 1, which is 0. Okay, so what is this? Just a0 plus 1 over a1. Hey, it works, because that's what this is, right? This is the continued fraction a0 plus 1 over a1. Question? No questions. Okay, now let's just do the induction. This is the fun part. We now have the base case of the induction. So now we're going to assume the proposition is true for n minus 1, and then we'll prove it for n. So we're assuming that we know this for smaller number. Well, I think we just need it for n minus 1, and then we'll prove it holds for n. Okay? Actually, for all continued fractions, basically b0 up through bn minus 1. So anytime you have a continued fraction and it has less terms in it, we can assume that this holds. It doesn't have to literally be the one right before. Okay? You can just assume it no matter, take any continued fraction at all, and if it has less terms, then this holds. Because we've checked it for the base case of 0 and 1. This holds for all continued fractions with 0 or 1 or 2 terms. Okay, so we have that, and now let's do it. So we just take a0 through an, and we're going to do, it's basically a trick. We'll rewrite this as a0 through an minus 2, and then so let's have to carefully check that this is correct. Let me make sure I write it exactly right. We're going to rewrite it as a continued fraction with one less term. An minus, so it's a0 through an minus 2, and then an minus 1 plus 1 over a sub n. Okay? So if you write out the algebraic expression on the left, it's the same as the algebraic expression on the right. And remember, the only requirement here is that the numbers we're considering are all positive real numbers, except possibly a0. So I'm going to just kind of quickly write out both sides somewhat, and then you'll see that this is obviously true, and then I'll erase that. Okay? So on the left-hand side, you have a0 plus 1 over a1 plus plus 1 over an minus 1 plus 1 over a sub n. Okay? On the other side, you have a0 plus 1 over, it looks the same at the beginning, plus 1 over plus an minus 2 plus 1 over, and now the last term is this whole thing, an minus 1 plus 1 over a sub n. But look, that's exactly the same. There's no difference. You can, basically, if you have this big continued fraction, you can view it as the very last term is an, right here, or you can just take this whole thing and view it as the last term of a continued fraction with one less thing in it. Okay? But that allows us to apply the induction, because all of the p sub n's and q sub n's for this guy up through, so these pi, qi, for I up through an minus 2, or for I up to n minus 2 are exactly the same as for this one. These two continued fractions start out the same. Okay, I'm going to erase the blue, and then I'm going to rewrite the thing on the right using this inductive step. Okay, so by induction, on this continued fraction, which has one less term in it than the other continued fraction, by induction, this is the appropriate quotient. It's so we have to write down for this continued fraction what that quotient would be, and it's what you do is you take the last term times the previous p's and the last term times the previous q's. The last term here is a n minus 1 plus 1 over a sub n times, now p n minus 1, except it's actually p n minus 2 because we're doing this for n minus 2. So that plus p n minus 3 divided by, again, a sub n minus 1 plus 1 over a sub n, q n minus 2 plus q sub n minus 3. I think that's the only hard step in this proof. The rest is going to be completely straightforward algebra. We just expand that out, use the definitions, and we get exactly what was claimed. So let's let you think about it for a second. All I've done is written down the definition of these two and noted that it's really the n minus 1 term that we're talking about here. So you have to put n equal to n minus 1 in this formula. I'm just going to count to 20 in my head while you look at this. Good? Good. Okay, now let's do the rest. So now it's kind of natural what to do. We're just going to kind of multiply top and bottom by a sub n, and then expand it out, and then simplify it, and we're going to end up with something that looks like that over that. Okay? So let's do that. So this, by multiplying top and bottom by a sub n, is a sub n minus 1 times a sub n plus, let me be careful, times p sub n minus 2 plus p sub n minus 2 plus a sub n times p sub n minus 3. Correct? All I did was multiply the top by a sub n and just expand it out. And now the bottom, again, multiply by a sub n and expand it out. So I get a sub n times a sub n minus 1 times q sub n minus 2 plus q sub n minus 2 plus a sub n times q sub n minus 3. Okay, and now we're going to try to get something that's a n times something plus something else. So just factor out a sub n on the top and the bottom as much as you can and see what happens. And this works out really nicely. So I'll just rewrite this as a sub n times a sub n minus 1, p sub n minus 2, and there's an a sub n at the end, so that's plus p sub n minus 3, divided by, oops, I forgot a term, plus p sub n minus 2. Okay, and then divided by a sub n times a sub n minus 1, q sub n minus 2, plus q sub n minus 3, plus q sub n minus 2. Okay, now finally, look, that right here, this is exactly p sub n minus 1. And that's q sub n minus 1 by definition. So you get that this is a sub n, p sub n minus 1, plus p sub n minus 2, divided by a sub n, q sub n minus 1, plus q sub n minus 2. Boom. That's, well, just rewriting that, that's p sub n divided by q sub n. Okay, so the algebra works. And now, anytime, so you can think of a continued fraction as being some expression like this, but for every possible thing that we're ever going to prove, we're going to think of the continued fraction a0 through an. Its value is the quotient of Pn over Qn, where Pn and Qn are given by these two recursive formulas. And also, just conceptually, you can think of continued fractions are sort of like this weighted Fibonacci number thing. Let's see, weighted Fibonacci. And I encourage you to try taking this fraction like this, and just try truncating it. You'll find the numerators of the numbers you get out of this. They're the things right here. They are in fact Fibonacci numbers. Which is kind of neat. So that's what we just proved. We proved that. And also think about it. If the ANs are all 1, then you're basically getting the same sequence on the top and bottom, except one of them is one behind the other one. So, if you take quotients of successive Fibonacci numbers, you're getting approximations to the golden ratio. It really sounds like elementary number 3. Heard it? Okay, so any questions about this? So again, it's really, this is the main thing to remember right here. And I'll just have time. So there's something at the beginning, but Pn is An Pn minus 1 plus Pn minus 2, Qn An Qn minus 1 plus Qn minus 2, and you have this. So there you go. So you can think of continued fractions as being given this way or that way, but they're completely equivalent by basic algebra, which we just did, and induction. But if we didn't prove this thing right here and work with the Pn's and Qn's as I've defined them, we would end up with every single proof being some complicated thing like this, which we don't want. All right, so now let me show you something that gives much more of a feeling for how these Pn's and Qn's work. I'm going to prove that they satisfy, well, that they're co-prime. So Pn is co-prime to Qn. This is really in lowest terms. But the way I'll prove that's really neat. It shows you that if you take these numbers that I've written down, take like successive ones, you get 2 by 2 integer matrices with determinant plus or minus 1, which are not necessarily systematically easy things to find. So that's kind of nice to see. Okay, so probably be the last thing we have time for today, but proposition, if you take the determinant of the matrix Pn, Qn, Pn minus 1, Qn minus 1, then this is of course Pn, Qn minus 1 minus Qn, Pn minus 1 by definition, but here is the amazing thing, it's just always minus 1 to the n minus 1. Okay? By the way, this, by just dividing both sides through by Qn times Qn minus 1, you end up getting the difference of successive convergence to the continued fraction. So if you have a really long continued fraction and you cut it off at some point, and then you cut it off one more, then you might be interested in what the difference of those two are. How much is the continued fraction changing as you're adding in each additional term? And this formula, if we can prove it, all you have to do is divide both sides by Qn minus 1, gives you a bound on the difference of the successive convergence. And that will allow us to prove something about how good continued fractions are at approximating numbers. So I just want to remark why this is cool. So why useful? One reason it's useful. Just divide both sides. So you get Pn over Qn. You're dividing both sides by Qn minus 1. Minus Pn minus 1, Qn minus 1 is equal to minus 1 to the n minus 1 over Qn minus 1. So that's why we care about what I'm about to prove. There's one reason. it tells you a lot about how the successive convergence compare to one another. You see, for example, that the sign is changing every time the sign changes. That tells you something about convergence, and also this tells you a lot about the size of the difference. Okay? So let's prove this. And it's like 2 lines. So first, it's going to be an inductive proof again. And we'll do the base case of n equals 0. And then once we have that, we'll be able to prove it in general by knowing it's true for all smaller n. Okay? So first, for n equal to 0, well, let's see, what do we have here? P0, it's just P0, so it's just a matrix that has, it's like this, but in the other order. So it's the determinant of the matrix A0, 1, 1, 0. And the claim is that that is -1. And it is. So, good. So, oops, yeah, A0, 1, 1, 0 is equal to -1. Okay, so now let's do the general case. So, suppose n is greater than 0 now. And this statement is true, and proposition is true for n minus 1. Okay? So now we just need to prove it for n. And I mean, it's really follow your nose, this argument. All you do is you just write down the thing that you want to compute, and then you substitute the definition of Pn, which involves smaller p sub n minus 1 and p sub n minus 2's, and the same with Qn. You just substitute those in, expand, and use that the statement's true. I mean, it's the most straightforward follow-your-nose induction possibly imaginable to prove this. Okay, so let's do it. Pn Qn minus 1 minus Qn Pn minus 1. This is the thing that we want to compute. We want to know what this is. What is this? Okay, so Pn is, by definition, An Pn minus 1 plus Pn minus 2. And we know all about what happens with these smaller ones. So it's just going to work. So Pn is An Pn minus 1 plus Pn minus 2. Remember, it looks like a Fibonacci number, but there's an A in there. Times Qn minus 1 minus A sub n Qn minus 1. So just substituting in Qn, I'm rewriting Qn as An Qn minus 1 plus Qn minus 2. That thing times Pn minus 1. Right, first, we're really fortunate, something cancels. Look, you have An Qn minus 1, Pn minus 1, the negative, and you have exactly the same thing over here. So that's nice. Do you see that? This cancels with that. So the thing that involved a product of 3 things, it just cancels out on both sides. So this is just the same as Pn minus 2, Qn minus 1, minus Qn minus 2, Pn minus 1. But hey, that's almost exactly the thing that our inductive hypothesis is about. It's actually the negative of the thing that our inductive hypothesis is about. Qn minus 2, Pn minus 1, minus Pn minus 2, Qn minus 1. I just rewrote that with a negative sign out front. But our inductive hypothesis is that the statement that I have is true for smaller values of n, so I just have to put n minus 2 here. And basically, this statement with n replaced by n minus 1 on both sides is true. But that's exactly what I need to simplify this. And so I end up with minus 1 to the n minus 1. But that's the claim, so we just proved it. There's a similar statement whose proof is exactly the same. And I'll write that down for the record because we'll also want to have it. namely that Pn Qn minus 2 minus Qn Pn minus 2. This is minus 1 to the n a sub n. Okay? And the way you prove this, not surprisingly, you check it when n equals 0. Then you just take this thing on the left, replace Pn and Qn by what they are, and then do the and assume the inductive hypothesis, and it just works. Okay? So a similar argument. So also prop. Ooh. Okay? And now, as a corollary, the 30-second corollary, let's conclude that if the a sub n are all integers, then of course the p sub n are integers, and the q sub n are integers. That's obvious. And the GCD of Pn and Qn is 1. That's not quite so obvious. So obviously, if the a sub n are integers, then the p sub n's and q sub n's are integers because of the formula. They're just linear combinations of integers. That the GCD is 1, well, imagine you had a common divisor of Pn and Qn. Some number, some prime, say, that divides Pn and Qn. Well, then it's going to divide Pn and it's going to divide Qn, so it's going to divide this difference. So it's going to divide a power of minus 1. So it's 1. So that's easy. Right? So the theme right at the beginning next time will be why every number has a continuing fraction. Yes?
Oh,
sure. Let me turn this on.
The part 2 of homework number 1.
Yep.
So I'm doing that by like I